ionic compounds. This is section 3.7. How do we first form ions? If this is our periodic table, and these are our main groups, so groups, periods. If we look at the first two groups, they have low ionization energies. From the previous section that we looked at, the trends in ionization energy, these two groups will have the lowest out of the whole periodic table, which means that because they have low ionization energies, it doesn't take very much for them to lose that first electron or second electron. So let's look at the periodic table in a slightly different way, right? It's not laid out square or a rectangle, but it's in a circular way, if you will. So it's a spiral. And here's my group 8. This is my noble gas configurations. These are the configurations that every other element in the periodic table is trying to reach, trying to get to. These noble gases are the island of stability, right? Everything is going towards that because this is the stable configuration. And every other element in the periodic table wants to reach this configuration and wants to do it, so it does it by either gaining or losing electrons. If the ionization energy values are low, it's going to lose electrons because it's very easy. Once again, the ionization energy, the lower the ionization energy value, the easier it is to remove that first electron. The higher the ionization energy values, the harder it is to lose electrons. And so those types of ions or atoms like group 7, for example, which have very high ionization energies, are not going to lose electrons because the energy that you need to put in is much more than the stability they're going to get. They're not going to be stable by losing an electron. So how do we make positive ions? Once again, remember that we're trying to get to noble gas configuration. So how do these elements over here, which is the group that has the smallest values for ionization energies, how do they become like the noble gases? Well, here's my lithium. It has this electron configuration, 1s2, 2s1. So lithium has 3 protons and 3 electrons. Here's my 3 electrons. There's 2 in the first shell and 1 in the second, right? The second level. So now lithium has, we said, it has a low ionization energy value, which means it's easy to lose that 1 electron. And if it loses this electron, then its configuration becomes 1s2 because we'll only have 2 electrons. If it's 1s2, that is the same configuration as helium. Therefore, it loses 1 electron, meaning it gains a positive charge because now it has one more proton than it does electrons, right? It still has 3 protons because it's lithium. It hasn't changed. Remember when we talked about the fact that both lithium atom and lithium ion will have the same number of protons. They will just differ in the number of electrons. And lithium atom has 3 electrons. Lithium ion has 2 electrons and 3 protons. That's why it has a +1 positive charge. All of these remember we said that all of the group 1 will be filling the s subshells, and they will have 1 electron in the subshell. So lithium reached the helium configuration by just losing 1 electron. If you look at sodium, which we did, sodium has 11 electrons. it loses that one electron to get to neon configuration, which is 1s2, 2s2, 2p6. Neon configuration, 10 electrons. So all of these, they're basically one electron removed, or one proton, one electron removed from the noble gases. Therefore, all they have to do is lose one electron to get to the helium, to the noble gas configuration. Now, let's look at it from this perspective. So these groups, all they have to do is lose electrons and they go to the previous noble gas configuration. So we figure out, okay, lithium is right here. What is the previous noble gas before lithium? That's helium. So it loses enough electrons to get to helium. Sodium is, so we go down to sodium. What is the noble gas right before sodium? That is neon. So sodium loses that one electron to get to the noble gas that comes right before it. Potassium comes right after argon. That's the noble gas, and so it loses the one electron that it needs to get to 18 electrons that argon has, and so on and so forth. You can follow this around. Now, if we talked about the second, so this is my group 1. Group 2, and I'll go back here, group 2 is right here. It's 2 electrons removed. So it needs to lose, if it loses 1 electron, it gets to lithium, for beryllium, for example. If it loses 1 electron, it gets to lithium. So it needs to lose 1 more to get to helium. So it has to lose 2 electrons. These would have to lose 3 electrons, and so on and so forth. So group 1 elements, to get to the noble gas configuration, they only need to lose 1 electron. Group 2 elements will need to lose 2 electrons to get to the noble gas configuration. That's why group 1 will always form a +1 ion, and group 2 will always form a +2 ion. So if I told you what's the ion that potassium forms, you will look at it, oh, it's group 1, so it forms a +1, K+. That is always the ion that potassium will form. Calcium will always form a 2+. Why? Because it's a group 2 ion, and all of those elements will lose 2 electrons to get to the noble gas configuration. So calcium will have a 2+. Positive ions, we call these cations. Don't know where the cat came from, but they're called cations, and they possess a positive charge, obviously. We name these ions according to the name of the element: potassium ion, sodium ion, lithium, beryllium, magnesium, etc. So they are named after the parent element. Now let's look at these, the nonmetals. If you remember from the ionization energy table, they have very high ionization energies, high ionization values, which means that it is very, very difficult for these elements to lose an electron, to form positive ions. Therefore, they do not form positive ions. So what kind of ions do these form? Well, let's look at our spiral, and let's talk about how we make negative ions. Once again, this is the configuration that we're trying to reach, okay? And this is the noble gas configuration. Now, these elements are if you're just looking at it, are to the left of the noble gases. So how do they become like the noble gases in configuration? We knew that these that came to the right of the noble gases had to lose, these would lose 1, these would lose 2, these could lose 3 to get to the noble gases. But what about these that are on the left side? How do they become like the noble gases? Here is the configuration for fluorine. Fluorine is right here. It's element number 9, so it has 1s2, 2s2, 2p5. What is the next closest? What is the closest noble gas to fluorine? If you look over here, fluorine is 9. Well, number 10 is neon. So neon is the closest. And neon has the configuration of 1s2, 2s2, 2p6. So the difference between fluorine and neon is just one electron. Fluorine has one less electron than neon does. Therefore, all fluorine needs to do is take one more electron to get to 1s2, 2s2, 2p6. And it does that. And here we go. It gets this configuration, which is the neon configuration. And it does this by gaining one electron. And if you gain an electron, that means you will have an excess of positive charge, an excess of negative charge, I'm sorry. And the number here will tell you how many electrons you've gained. So fluorine only has to gain one to go from 5 to 6, and therefore it forms a -1 charge. This is true for all of these. Well, hydrogen doesn't really count much, but it will form a -1 hydride. But all of these halogens, so group 7, which are right next to the group 8 noble gases, just to the left of them, all of these ions or elements, they only need one more electron to get to the noble gas configuration. So all of these will form a -1. They'll form a -1 ion. So the halogens, group 7, form a -1 ion. If we are in group 6, oxygen, for example, group 6, they need one electron, two electrons. So oxygen, if it gains only one electron, will become like fluorine. So it needs one more to get to the noble gas configuration. Therefore, these group 6 elements will always form a 2- because they need two electrons, two extra electrons, so 2- charge. Nitrogen and phosphorus are group 5. They'll need 1, 2, 3 electrons, so 3- charge for group 5 elements. So here we go. We have the halogens, which is group 7. They're only one removed, so one place removed from the halogens or the noble gases, so they only need one electron. That way they form a -1, always form a -1 ion. Group 8 or group 6, and we're only going to talk about oxygen and sulfur mainly, but group 6, that's the rule that elements in group 6, they need two electrons because they're two places removed to the left of the noble gas group, and therefore to reach to noble gas configurations they need to gain two more electrons, and therefore they always have a 2- charge. And we also mentioned group 5, which is, we're going to really deal with mainly with nitrogen and phosphorus, but group 5 is 3 places removed from the noble gases, so they need 3 electrons to get to noble gas configuration, and therefore they always form 3- ions. Negative ions are called anions, and they're named slightly different than the cations. They're named by the first syllable of the element name, and then we truncate it and we add the IDE ending. They obviously carry a negative charge. For example, how do I name the anion of fluorine? I take the name of the element, fluorine, I truncate it, and I add IDE to it. So fluoride. Instead of fluorine, I cut the in off and I add the ide. Fluoride, chloride, bromide, iodide, oxide, sulfide, etc., etc. So this is how we cut off the name, part of the name of the parent element, and then we add the IDE ending. Now, we can have two different types of compounds, the ionic compounds and the covalent compounds. Very important distinction to tell whether you have an ionic compound or not. they're made of cations and anions. And if you looked at how we how we how we made positive and negative ions, the cations were formed from the metals and the anions were formed from the nonmetals. So if you have a compound where you have the positive ion that it's a metal, obviously it's a metal because it's a positive ion. If you see a metal and a nonmetal, that will tell you that you have an ionic compound. These ionic compounds are held together by ionic bonds, which is the attraction between the opposite charges. You have positive ions and negative ions. Obviously, they attract each other. Opposite charges attract, and then they're called, so that attraction is called an ionic bond, and that's what holds together ionic compounds. It can be a very, very strong bond. Some of these ions have very high melting points and boiling points because those bonds are very, very strong ionic bonds. And ionic compounds then, as I said, are composed of a metal and a nonmetal. There can be exception, but in general, they're a metal and a nonmetal. They're very crystalline in nature. They form crystals, very ordered crystals, and have a very high melting point. That's because those ionic bonds are very strong. So if you have a formula of a compound and you see that typically the first element that is listed is the metal. So if you look at the first element in a compound and you see that you have a metal, that means you have an ionic compound. The chemical formula is the lowest whole number ratio of atoms or ions. This is true for any of ionic compound, any salt. It's the lowest whole number ratio of the atoms or ions. So if I have NaCl, that means I have a 1-to-1 ratio between sodium and chloride anion. I cannot write Na2Cl2. That is not, it has to be the lowest ratio. So if I want to say I have 2 molecules or 2 moles, I would put the 2 in front of the NaCl, not as a subscript, because that we have to have the smallest whole number ratio between the atoms or ions in an ionic compound. So here it is. Here's how we take ions and we form an ionic compound. The idea behind this is that when we form ionic compounds, they typically are neutral in charge. Therefore, my total negative charges have to equal the total positive charges. In this case, because I have a +1 and a -1 charge, if I just put these together, then I just form NaCl, and it's a 1-to-1 ratio because I have a +1 and a -1 and they cancel each other. So if I write the compound the way it is, that means it's a neutral compound. I don't have to do anything to it anymore. Now what happens if these charges don't match? For example, what if I have this example here? So I have a +2, magnesium +2, and then I have a chlorine -1. Well, if I just write MgCl, that will not give me a neutral compound because I will have a leftover a +1 charge. To balance that out, I need to have 2 chloride anions. And notice that we write the subscript next to the ion. We don't write it in front here because if I wrote it in front, that means that I would have 2 magnesiums as well. So if we want to manipulate only one atom at a time or one ion at a time, I do that by writing subscripts close to each one. So to the right of each ion. I don't need to mess with magnesium because I already have a 2+ charge, but to balance that 2+, I need two chlorides, with each of them with a -1 charge gives me a total of -2 to balance that +2. And to write that 2, as I said, I write it as a subscript by the chloride. That tells me that I have 2 chlorides, but I only have 1 magnesium. If I put this 2 in front, that meant that I have 2 magnesiums and 2 chlorides, and I still would not have the charge balanced. I'd have a -1 and a +2. If it is just if the subscript is just 1, we do not write it, just like we did with NaCl. We just do not write the 1. Or with magnesium here, I don't write the 1. So if it's any greater, if the subscript is greater than 1, we must label it and we must write it to the right of that particular ion. I have provided you with examples on how to write a chemical formula if you're given the names of the element. So I've done this problem and I've also done this problem. So check those out and figure out how to do that. For these, you will have to learn the name of the elements, and by figuring out what group they belong to, you will figure out what ion they form, and you also will have to learn the names of the polyatomic ions and their charges to be able to do these types of problems. You have to memorize them. There's no way around it. But look at these problems and let me know if you have any questions. We'll do a bunch of other examples in class as well. Now, what's interesting, I mentioned earlier when we were looking at the divisions of the periodic table, we had this block here, what we called the transition elements, and I said they're kind of the unruly kids. We said that, group 1 and group 2, they form +1, +2, so they only form a single ionization state, meaning a single ion. They do not form multiple ions. The group 1 will always form a +1, so it has a single ionization state is what we say. All nonmetals have a single ionization state, meaning they will always form the same anion. This group will always form a -1, this group always a -2, these two always a -3, etc. But not all metals have a single ionization state. Not all of them form the same ion. The ones that are labeled here, those metals, will always form the same ions. So group 1 and group 2, and then there's these exceptions here. Aluminum forms a +3, and then zinc and cadmium, these two form a +2, and then silver has a +1. However, all the rest of the metals might have more than one type of ion that they form. For example, iron can form a +2 or a +3. Copper can form a +1 or a +2. Chromium can form several, +2, +4, I believe in a +6, and so manganese as well. So these transition metals will form several different kinds of ions, and depending on what the molecule is, they can have a different charge. So we cannot really look at the transition element and say, iron is a +2 because it's a +2. No, it could be a +3. So to determine the charge on the ion that is formed from the transition elements, we must look to the nonmetal first, because they will always form the same type of ion, and that will dictate what the charge will be on the transition metal. Now, for polyatomic ions, you will have a list of them to remember. These ions are formed from atoms that are bonded covalently to each other, so not really from ionic attraction, and then the whole unit has an overall charge. For example, if I'm talking about NH4 plus here, this +1 charge doesn't belong just to nitrogen or just the hydrogen, or to any of the hydrogens, because there's 4. This +1 is distributed over all of this molecule, NH4, so over all of it. So I cannot just talk, when you have polyatomic ions like this, you cannot say, well, nitrogen has a 3- and hydrogen. No, this is the +1 is over the whole molecule, and consider this as one unit. You cannot separate these elements. They are covalently bonded to form this ion, the polyatomic ion, and that charge goes with the whole unit, not just with the hydrogen or the nitrogen. Most of the polyatomic ions we're going to talk about are anions. They're negatively charged, and they contain oxygen, so they're called oxoanions. oxo from oxygen and anions because they're negatively charged. And the exception to that is the ammonium ion. The ammonium is the only positive ion, a polyatomic ion we're going to talk about. And note that we don't write the plus 1 here because it's assumed that it's a 1. But NH4 plus is the only really positive ion, polyatomic ion we're going to talk about. Once again, as I said, memorize the list, memorize the names, the formulas of the polyatomic ions, and the corresponding charges. They will be very handy if you learn those on how down the road when we learn how to write formulas and even how to balance chemical equations. It will be important that you know the names, you know the charges, you know the formulas for these. Okay, this is the end of the ionic compound section. And then the next section, we're going to talk about the molecular compounds and work some examples.